heat engine, thermodynamics, heat engine. Okay, so this is the fundamentals basically. So one of the three important variables which are correlated in heat engine is delta Q, which is the change in amount of heat in the system, is equal to delta U, change in internal energy, plus delta W, the amount of work done. Okay. In case of heat engine, it does the work on the surrounding. In case of heat pump, work is done by the surrounding on the heat pump. So we're not dealing with enthalpies, and the change in internal energy of the system is negligible, so we approximate delta U to be 0. So we get the form delta Q is equal to delta W, which means Q1 minus Q2 is equal to delta W, and Q1 is equal to delta W plus Q2. Okay, so this is a form to begin with. Rather heat content 1 minus heat content 2 is equal to change in the amount of work done, or basically the net work done. Okay, and also there is a factor there's a parameter efficiency, which is equal to work by input. So in our case, the work done is delta W, and the input into the system is the heat content, which is Q1, or can be Qn also. Qn, now we make the substitution from 1 in 2. So eta efficiency is equal to Q1 minus Q2 by Q1. Yes, so eta is Q1 by Q1 minus Q2 by Q1. Yes, which means eta is equal to 1 minus Q2 by Q1, or eta is equal to 1 minus Q out, heat rejected to the surrounding, by Q in. Okay. And in some cases, I will show you how. I will show you. In some cases, we need the form in terms of temperature. So eta is equal to 1 minus Q2 by Q1, but delta Q is also equal to NC delta T. Q can be approximated to NCT, where NC is roughly a constant. So Q can be approximated to T. Yes, let's call it capital T here. So eta is equal to 1 minus T2 by T1, or eta is equal to 1 minus T out, temperature of the surrounding, by temperature within the system, T in. Yes, so these are also forms. So basically, schematically putting it, source of heat is somewhere here, and we have a system working here. Yes, this is the system. and now we have the sink here, sink. So what we get from the source is Q1 at the heat end, and what we put out to the sink is Q out, Q, which is Q1 here and Q2 here. And what the system does in this case is the work. Okay, this is to schematically represent the heat engine. And if we are to reverse the situation, and if we are looking into heat pump, and the situation reverses, heat pump, source, sink, work is done on the system. This is the system here. Q in is taken by the system and Q out is rejected. Q1, Q2, in other words. Okay, so the efficiency of the system is work done by input, roughly it is equal to work done in this case work done in this case is so basically the efficiency for a heat pump would be heat extracted by the surrounding divided by work done on the system to extract that heat. Okay, so in this case let's call it source, once again source, sink, work done on the system, yes, and heat taken by the surrounding, which is Q1, and also there will be a waste Q out because no engine works with total efficiency, so there's always a loss, so there's always a sink. Okay, so a bit of a correction and explanation of the concept. And eta is equal to Q1 by W, and W is equal to Q1 minus Q2, and eta is equal to Q1 by Q1 minus Q2. And in terms of T, the temperature, the efficiency would be T1 by T1 minus T2. Yes. And now we get back to the refrigerator. In this case, we are discussing a refrigerator. In this case, alright, let me remove the heat extracted by the source, or the heat rejected to the surrounding could very well be the deciding factor for cooling. In case of refrigerator, the work done is Q1 minus Q2. Yes, because an efficiency is the amount of heat rejected to the surrounding refrigeration by the work done. Okay, and the heat rejected happens to be Q2, which gets rejected out of the system. Okay, so we put it like this: Q2 by W, or Q2 by Q1 minus Q2, and in terms of temperatures, T2 by T1 minus T2. This is also writable because we have already approximated Q to be T, because NC is uh, constant. Okay, so all right, we don't go into details, and now we look into the Carnot engine. Carnot engine, and the efficiency is output by input. And clearly the efficiency is output is the work done by the system, and input is the heat given to the system, Q1 or Qn. So, and W is equal to Q1 minus Q2. W is equal to eta is equal to Q1 minus Q2 by Q1. So this is the forms, and in terms of temperatures, T1 minus T2 by T1. Temperature of the uh, uh, temperature of the system, temperature of the surroundings 2, and sorry, uh, temperature of the source T1 and temperature of the sink T2, because there's a difference between the heat contents. Q1 is the heat content of the source coming from the source, and Q2 is the heat content going into the sink. Okay, so these are important to keep in mind, and we can approximate them to temperature as well. Once we have the form for eta in terms of Q here, we can also replace Q by T, and if somebody is interested in further alterations, the inlet and outlet heat contents or temperatures with the Q in or Q out or T in or T out symbols can also be used. So just to show once again, we have this source gives us some heat content. Here's the system and here's the sink. Okay, so for refrigeration, work is done on the system. This is for refrigeration, and the heat is extracted by the source, which happens to be Q1, which happens to be Q, and okay, Q heat extracted by the source Q2 and heat rejected into the sink Q1. Q2, sorry, Q1 here and Q2 here. If we change the signs, for example, if we reverse Q1, Q2 here, then we also reverse the Q1 and Q2 here, which changes the form of the equation. So we call it A here and we call it B here for Carnot. And in terms of Carnot, you'll see for Carnot cycle, see the source, let's say, is here and the sink is here and the system is here. Yes, so now the difference is that the system is now doing work on the surrounding, and it is taking heat, one from the source, and rejecting the remainder, two to the sink. See the direction, the direction of the arrow indicating the work done by the system as compared to the one on the system in refrigeration. So this is the schematic difference between the technical one between engine and refrigerator. Notations can change, and so the forms change with notations.